My name is Akin, and today I'm going to talk about speed measurement using optocoupler experiment. I'm going to demonstrate it. So these are the apparatus required for the experiment. This is an oscilloscope to get the output waveform. This is the speed measuring circuit to measure the speed or RPM. And this is a multimeter to get the input voltages to a motor. This is the motor fitted with 15 slotted disc, and also the black component is optocoupler used for speed measurement. Coming to the V part, here we can see the optocoupler circuit, and on the right side we can see the optocoupler device agent, and it is a basic device which is makes use of an PIR sensor. So here is the input curves, input source or the source, IR source. So when a current is passed through this circuit one, there will be an IR radiation produced, and this will fall into the phototransistor, which will result generation of current in circuit. Uh, this is how the circuit works. And here we can see the device. And in the right side, we have the basic reason of the couplet. And here the LEDs and like M source, which is generally of IR radiation. On the right side is the phototransistor that detect the transit radiation. Generally, these are enclosed in a resin or some kind to protect them from air. First one, the circuit, then change the input of the oscilloscope to the wave shaper and set the counter switch to RPM. I'll increase the voltage to a certain value where the motor starts rotating, or any certain voltage. Now we can see the motor rotates and the voltage to be 0.245 volts. And now we can see that there are a square wave patterns here. And each square wave is generated because of a slot in this. And you can see the frequency of the waveform. We'll note out this frequency for each of these different voltages. And now we'll change the counter switch to speed. And using a timer of 10 seconds, we'll take the number of counts and we'll note it down, the number of counts for each of the different values. Now reset the counter switch, set the voltage to 0, and change the input to the multiplier. Continue the same experiment as before, and take down the multiplier readings for each of the different voltages. As we have seen from the experiment, we have taken two values. One is the multiplier output and the other is wave shaper output. But why did we take the multiplier output? We'll discuss it in this. So like the multiplier output be F hertz. Now, so the wave shaper output will be F by 4 hertz. So calculating the number of rotations per second, as each rotation consists of 15 pulses. So F by 14, F by 4 into 1 by 15, we'll get the number of rotations per second to be F by 60. To get the number of rotations per minute, we need to multiply it by 60. So multiplying in the 60, we'll get the rotations per minute to be F, which is the multiplier output. So we have calculated the multiplier output so that we can directly calculate the RPM of the disc, which is used in speed calculation. Here are the results for different voltages. So this is the wave shaper output. This is the output for multiplier, and here the RPM that is shown in the speed measurement circuit. So as we can see that as the voltage is increasing, the frequency of the wave shaper increases, which means the RPM increases or the speed increases. You can also observe that the multiplier output and the RPM are nearly equal. Here we can see it's 521 and 535, and that the last is 1.7 on charges. This small error is because of the Hinlock error, and generally it needs to be similar to that of RPF. This is why our calculator or measure the 4 times multiplier output so that we can directly measure the RP. Slide, we discussed how to measure the speed of the disk. We know that the diameter of the disk to be 85 mm. Now calculate in the circumference of the disk by using the formula of 2 pi r or pi d. Then get the value to be 267.035 mm. Now the disk consists of 15 slots. Now we'll calculate the distance traveled for each slot or per slot, and it is given by circumference by 15. So we get that the distance traveled in each slot to be 7.8. Now to calculate the speed, we need the number of counts that we have taken from the experiment, and the total time is said to be 10 seconds that we have taken. And using this formula, number of counts per total time into 17.8 mm per second, we will get the speed measurements. Here are the speed measurements for different voltages. So as the voltage increases, we can see if the speed increases. These are the counting readings that we are taking for 10 seconds. And using the formula that we have derived previously, by substituting these values, we get the speed measurements. Coming to the precautions, there are 3 precautions that needs to be taken care to get an accurate result. The first one is to set the counter switch to speed before taking the number of counts, or else the number of counts set to be 0, or we don't get the number of counts. Also ensure that all of the cables are connected tightly, mainly to the oscilloscope, as it is the main important factor in getting the accuracies. Also make sure that all of the connections in the speed measurement device or circuit is correct so that we get accurate results. So in this slide, I will discuss about the innovative idea that I've got. We can make use of the optocoupler switching mechanism as a switch. So here is the basic circuit diagram of the optocoupler. Here is the input of the indicators and in this output to detect the voltage. We will insert a material or high absorbability such that it absorbs all of the radiation fall onto it when the intensity is within the limits. So when the voltage is within the range, let's say 0 to 240 volts, the intensity of light emitted will all be absorbed by the material, causing no radiation to reach the detector. When such no radiation was detected, the output circuit, the device, the circuit will operate as it is. And when voltage is increased to 240 volts, the intensity of the light will be increased, making the light to pass through the material and gets detected at the detector. Now we will design the output circuit in such a way that when the light is detected, the output circuit needs to be turned off. So in this manner, we can design the optocoupler to act as a fuse. Thank you.